Hi guys, this lecture is just a review of ways to solve for that pesky electric field. And the objective is basically to introduce the importance of Laplace's or Poisson's equation in electrostatics. Okay, so our main objective in electrostatics, or kind of in E&M in general, oftentimes is to solve for the electric field of a static charge distribution. So that's what we want to do. There's a lot of examples where we might want to do this. I often think about instrumentation. We often use electric fields to push particles around or do work for us. I always think the electric force is interesting and powerful. It's much stronger than the gravitational force, of course, but we can also create force fields, right? We can't really create gravitational force fields as people, but we can put charged plates together, charged rods or whatever, and actually create a electric field situation where we could use it to, for example, print ink on a piece of paper like an inkjet printer, or for spacecraft, we often use electric field to push charged particles certain ways in instruments in order to detect them. And certainly there are some examples of that kind of instrumentation, not on a spacecraft, but in Discovery Hall. Some of the geology labs have mass spectrometers in them, and those mass spectrometers are using electric fields to push particles around the instrument chambers. So we often want to set up some kind of static charge distribution to create an electric field to do our bidding for us. So that's why we're so interested in being able to solve for what it is in space. Okay, so let's just review some of the ways that we've solved for electric fields in this class so far. The first way we learned about, and possibly one of the more challenging ways, the most challenging way potentially, is to use Coulomb's law. Okay, which can be written in this form here, where the electric field can be discovered through what we call direct integration, or integrating over some charge distribution, either in 1 or 2 or 3 dimensions, right? And you guys have experienced that this integral can be a little bit challenging to correctly set up. And once you do set it up, it can be even more challenging to actually solve it by hand, and it can even be challenging to solve it on a computer, right? Even Mathematica sometimes would take a long time to crunch through one of these integrals. Okay, so I would say that even for simple, which is all we really dealt with, charge configurations, idealized ones like spheres and planes and lines, this integral is challenging. And of course, in some cases, we can cheat with Gauss's law. But those are highly idealized as cases. Of course, you might think, why am I even bothering to learn this? Well, again, back to the idea that humans can often come up with the apparatuses to make the electric fields. Oftentimes we do pick planes of charge and lines of charge and spheres of charge to build our electric field. So actually these, even though we seem like we're just dealing with simple shapes, it actually is somewhat useful in the real world. Of course, if we're dealing with real systems like ionospheres and things like that, it gets a lot more complicated. Okay, so what's another option that was a little bit easier? If you guys remember, the next thing we learned how to do was we could still use direct integration, but now we could find the potential, and then we could use the potential to solve for the electric field, because we knew the negative gradient of the potential was equal to the electric field. And again, the way that we learned to solve for that potential was of a continuous charge distribution was through, again, direct integration. But this integral was a little bit easier to do because it only has one component. You don't have to worry about vectors and directions, and that made it a little bit easier. Okay, but it was still hard. All right, so it's easier but still hard. Okay, and few integrals could be solved analytically by hand or otherwise. And I think sometimes it's surprising to students to know that you can set up an integral that actually doesn't have an analytical solution, which means that if I write an integral with a bunch of symbols, I can actually come up with an equation that is the solution to that integral. I can solve it numerically if I can put numbers in, values in, but I can't get a nice closed form solution. And there's a lot of integrals in the real world when we're dealing with real systems that don't have an analytical solution. Okay, so the idea is oftentimes, again, in real life, if you're going to use a computer anyways, you might as well solve Poisson's or Laplace's equation. So this we're going to pose as being one of the most useful ways to solve for the potential, which again, you can then just take the gradient for to get the electric field. And in reality, this is one of the most common ways to actually do it. Okay, so let's just review that. Poisson's equation, that tells us that what's called the Laplacian, if you guys remember this guy, named after a mathematician, the Laplacian of, let me make sure it looks like a V, of the potential is equal to the negative gradient of the volume charge density divided by epsilon naught. Okay, that's Laplace's equation. A special case, that's Poisson's equation. A special case of Poisson's equation is known as Laplace's equation. And that's the equation that we use when we're in a region of space when there is no excess charge around, or we have a rho equal to 0. Okay. I can rewrite that by just writing out what the Laplacian is. Okay, so that grad squared. And these are all partial derivatives that I'm writing out, which basically means I'm just going to take the derivative of that potential V in one dimension at a time. Okay, so that's something to note. So they're different than total derivatives. Okay, this is what it is in Cartesian coordinates. As you guys know, oftentimes you have to apply these equations in other coordinate systems if you want to know the potential or the field in another coordinate system. So I'm not going to write down all the formulas because they're all in the back of your book, or you can find them easily with a Google search. But you might find it useful to also know what Laplace's or Poisson's equation is in spherical or cylindrical coordinates. Okay, and of course, once you know once you solve for the potential, you can find E in the same way by taking the negative gradient, which is going to give you a vector of the potential. Okay, and it's worth again notice, since we're still learning this is a scalar, right? The potential is a scalar. And it's also worth remembering when we're thinking about setting up these problems to know that it is constant on conductors. So conductors are what we call equipotentials. Okay, and even though it seems boring, oftentimes, like I said in the beginning, we're often more interested in solving for the potential in regions where there is no charge density or where rho is equal to 0. And the reason for that is we might set up, like I said, like a series of charged plates or something like that to create an electric field. But we don't really care so much about what the electric field is on the plates, right? It would be 0 if they're conductors, but we're not setting up like a bunch of point charges all over, and we're worried about that. Maybe we set up these plates to create an electric field in free space in between them, and we care about what the electric field looks like, right, in between the plates. But in between the plates, we have a situation where the charge density is 0, okay? So it's more appropriate to use Laplace's equation to solve for what the electric field is in that empty space.